Example, how many problems are completed yesterday? How many example problems are completed yesterday? Okay, it is the next problem. A system consists of two blocks of masses. A system consists of two blocks of masses M1 and M2. A system consists of two blocks of masses M1 and M2. Here it is M1, here it is M2. Okay. Here a system consists of two blocks of mass M1 and M2 connected by a spring. Connected by a spring of spring constant capital K. The block M1 is pushed down with a force, constant force F as shown in the figure, for which the lower block M2 just lifts after the force F is removed. Then F is equal to question mark. When for the load M2 to be removed, lift for load F2 to be removed, for the load M2 to be removed, for the load M2 to be removed, to be lifted, F minimum is equal to question mark. Okay, now all of you see the diagram. All of you see the diagram. Yeah, M1 plus M2 into Z. Very good. Here you see there are two blocks M1 and M2. Here these two blocks are joined by means of a light spring. Whenever the blocks are like this, the spring is in unstructured condition. Whenever the blocks are here, the spring is in unstructured condition. All of you stop your video sharing. All of you. So whenever the blocks are like this, the spring is in unstructured condition. So on this position, here on the block of mass M1, a constant force F is applied and it is pushed down, so that there is some compression in the spring. Here, actually, it is the natural length. This is the natural length of the spring. Natural length. That means there is no extension or compression. Natural length of the spring. Okay. So here, whenever the spring is in natural length, having natural length, at that time, the block M1 is pushed down with a force F, so that the weight of the block acts vertically downwards direction, and the force applied also acts downwards direction, so that the block displaces. In first position, the system is like this. In the second position, the block M2 is on the floor only. M2 is on the floor only, but when this block M1 is pushed downwards with a force F, and because of weight M1, the block displaces through certain distance downwards. So what is the displacement of the block? Means the block displaces from this position to this position through certain distance, say x1. Through certain distance x1. Okay. Here, because of this constant force applied on the block M1, the block displaces, this upper block displaces through certain distance x1, and the block is on the equilibrium now. At that time, what is the minimum force to be applied on the block M1, and it is pushed, so that when you remove the applied force, immediately this block rises, and when this block rises here, then the spring force developed in the spring must lift the block M2. That is the case. So when you remove the force on the block, immediately in third case, the block on the floor is like this only. But when applied force is removed here, when F becomes 0 here, immediately the block rises, because whenever the spring is compressed like this, here whenever the block is displaced downwards by applied force here through distance x1, then the spring is compressed by x1. So some energy is stored in the spring. So when you remove the applied force, then immediately, because as the spring is compressed by a length equal to x1, immediately the spring force developed in the spring, the spring force pushes the block M1 in upward direction. So whenever the spring pushes the block upwards, then for this block to be removed and to be lifted, definitely this block, whenever the block is in whenever the block come back to the initial position, there is no rise in the, there is no lift of the block M2. Because whenever the block comes to this position, again it comes to unstretched condition so that no force is developed. But it is pushed downwards so that when you remove the applied force, then whenever the block lifted, whenever the block M1 lifted to a height, if the block comes to this position, there is here a spring is in natural length. Spring is having natural length. That's why no force is developed. But whenever it's pushed down to a distance x1 by applied force, and when you release them, if the spring pushes the block upwards so that it rises up to certain distance x2 from the original position, then spring is extended by length x2. No, at the time the spring force is developed in the spring, and that spring force developed f dash. The spring force developed say fs, and fs has to lift the block m2. That's why for the block m2 to be lifted by the spring, then spring force developed in the spring in third diagram. In third diagram, when you remove the force on the block, then the block rises like this, so that the blocks are like this. Whenever this upper block M1 rises above the original position, then only spring force is developed here, and that spring force pushes the block, pulls the block M2 upwards. For the block to pull upwards, definitely the spring force must be balanced at least equal to weight of that block M2Z. Here, whenever the spring force is developed here, at that time the exchange here, whenever the block is here, first block is here, it is an unstretched condition. Whenever the block rises above the original position, initial position of the block, then only extension takes place in the spring, and that spring force developed and pulls the block upwards. That's why here, suppose the block rises x2 distance above the original position, then spring extended by x2. That's why extension of the spring here is equal to k into, suppose the spring constant is k into x2. That's why the block must be raised above this original level to a distance x2 to lift the block m2 upwards. That's why in this case x2 is equal to m2z by k. This is equation 1. Now here we can apply the law of conservation of energy principle. We can apply the law of conservation of energy principle, or we can apply the work energy theorem also. So now in this problem here, you see, in first diagram, you see, whenever the block is pushed by applied force F, the block comes to this position and it is under equilibrium. At this position, the block comes to this position and it is under equilibrium. When you apply the force on the body, when you pushes the M1 force downwards, then the block comes to this position and it is under equilibrium. Under equilibrium, you see, F force acts on the body in downwards direction, and weight M1Z also acts in downwards direction. That's why net force acts on the block downwards is equal to F plus M1 into Z. Okay. At the same time as the spring is compressed, spring force in this case acts upward direction. Spring force say Fs dash. Fs dash acts on the spring upwards. Or you say it is spring force Fs dash. Okay. It is say Fs dash. So here it is Fs dash is equal to this one. So here Fs is equal to, in first case, whenever the block M1 is pushed down with a constant force F, as the block comes down to a distance x1, spring is compressed. Whenever spring is compressed, the spring force developed opposes the motion of the block. That's why spring force acts in upward direction. Even then, as the block is under equilibrium at this point in the presence of the applied force, F plus M1Z is equal to spring force acts in upward direction. That is Fs. So F plus M1Z is equal to Fs means K into, here the compression of the spring is equal to x1 now. Initially the block is here. When the block is displaced by a length equal to x1 because of this applied force, then the block is under equilibrium whenever extension is this way x1. When extension is x1, at that time spring force developed is equal to k into x1. At kx1, you see, here in case of block M1, the weight M1Z acts downwards direction, and on the block applied force F also downwards direction. But at the same time, when the block comes down to a distance x1, as the spring is compressed, the spring force developed in the block in the spring opposes the motion of the block downwards and applied the force in upward direction. That's why spring force is in upward direction. So because of this applied force, whenever the block is under equilibrium, then these two, upward force and downward force, are equal. That's why F plus M1G is equal to K into X1. Okay, this is equation 1. Say this is equation 2. Now, you apply the conservation of energy principle, or you can use the work energy theorem also. According to work energy theorem. So we have two equations. Next, according to conservation of energy principle or according to work energy theorem. Okay. So according to work energy theorem. So here you see, this is the position of the body. Say it is A, it is B, it is C. Say. So from this position, whenever the block is here, you take this as the reference line. Initially, in the system, if you take this as a reference line, only potential energy is stored in the spring. Okay. Now, this spring pushes the block upwards. So whenever the block is pushed upwards, the block raises up to a height equal to, you see, up to this one. That means x1 plus x2. Block raises up to a height x1 plus x2. So work is done by gravity against the gravity. You know, as the block is lifted upwards, work is done by the gravity and work is done by the spring force also. Okay. Here the velocity of the body is 0. Here also velocity of the body is 0. Here velocity of the body here is 0. Velocity of the body is also 0. Because just the body rises up to certain height so that the block lifts. That's why it has no velocity. So here according to conservation of work energy theorem, net work done by all forces is equal to change in kinetic energy Kf minus Ki. Of course, as U0, V0, change in kinetic energy is 0. What is the net work done? Net work done means here work is done by gravity plus work is done by spring force also. These are only because spring pushes the block upwards and the block raises against the gravity. That's why there are only two works. That is equal to 0. What is the work done by gravity? Here you see, whenever the block is released, when you remove the force acts on the body, immediately the block moves up to a height this one. That means x1 plus x2. x1 plus x2 height, it rises. That means against the gravity, the block moves upwards. That's why net work done by the gravity is equal to negative work done minus m1 g into x1 plus x2. It is the work done against the gravity. Gravity acts on this block downwards, whereas the block moves upwards. That's why the work done by gravity is negative now. So work done by the gravity is equal to negative there. Okay, next at the same time, work done by the spring. What is the work done by the spring? You see, from this position to this position, from this position to this position, as compression is there, from this position to this position, the spring force does the work on the block, which is positive. Because whenever the block is displaced through a distance x1, spring is compressed. And spring force pushes the block upwards now. That's why along the direction of spring force, as the block move up to this point, then work is done by the spring force is positive up to this. Work is done by the spring force is positive up to this. Okay, that's why positive work half k into x1 square. But after that, this x1 becomes 0. After this, x1 becomes 0. Then extension takes place in the spring up to a height equal to x2. This is the extension. Whenever extension takes place, then spring force acts on the block in downwards direction. That is Fs dash. So whenever extension takes place, or whenever this block M1 move above this line, then extension takes place in the spring. Due to that, the spring force acts on this block downwards. So above this point, above this line, or above this position, as the block rises upwards, spring force acts on the block downwards. That's why due to this spring force, work is done, which is negative on this block. That's why minus half k into, as the spring force does the work on the block against their motion up to a distance equal to x2. That's why work done by the spring force on the block is equal to half k x2 square. That is the net work done. No other forces are there here. No other forces are there. Okay? No other force acts on them. Only because of gravity, because of spring force, what is the work done we calculated? That is equal to change in kinetic energy. Initially, whenever the block is here, at the moment whenever this force is removed, at that time block is at rest. Here also block is at rest. That's why it is equal to change in kinetic energy 0. Okay. Now from this formula, so m1z into x1 plus x2, m1z into x1 plus x2 is equal to here. From this we had to eliminate this x1 and x2. You see, you bring this m1z into x1 plus x2 to right, then you will get plus m1z into x1 plus x2. Okay, that is equal to, you keep these two here only and you take k by 2 common. When you take k by 2 common, x1 square minus x2 square, no? Therefore, m1z into x1 plus x2 is equal to k by 2 into a square minus b square. So we can write x1 plus x2 into x1 minus x2. x1 plus x2, x1 plus x2 cancel. Therefore, from this formula you see, m1z, just to do cross multiplication, 2m1z by k, 2m1z by k is equal to, simply you have x1 minus x2. You have x1 minus x2. Okay, or you write here like this, or you write 2m1z is equal to, you multiply with kx, kx1 minus kx2. Because we are having kx1 value here now, kx1 is equal to f plus m1z minus kx2 means from this formula kx2 is equal to m2z, no? So you write m2z. Okay, therefore f is equal to, it is 2m1z. F we need. F is equal to 2m1z minus m1z, means m1z. Then you bring this minus m2z to left, then plus m2z. Therefore, F is equal to, you take z common, m1 plus m2 into z. So, with what force this block is pushed downwards, so that when you remove the force, the lower block just, it has to lift upwards. What would be the minimum force with which it is pushed? Means this is the minimum force with which the upper block is pushed, so that the lower block just rises or lifts. This is the problem. Okay. So it is very, very important problem, this model. No doubt. This board is clear to you or not? After, okay, Guru Pranit, I will unmute you. Speak with me. Guru Pranit, what is your thought? You share with me.
Hello, sir.
Guru Pranit, tell me.
అక్కడ బ్లాక్ డౌన్వర్డ్ ఎక్స్టెండ్ అయినప్పుడు స్ప్రింగ్ మళ్ళీ ఫోర్స్ ఇచ్చి మళ్ళీ పైకి పంపిస్తుంది కదా సార్ బ్లాక్ ని.
ఇక్కడ మన యాక్చువల్ గా వెయిట్ వల్ల కొంత కింద డిస్ప్లేస్ అవుతుంది. Initially, whenever the block is here, there is no spring force. Okay?
Yes, sir.
Because whenever the block is here, the spring is in natural length. That's why it has, in this spring, there is no spring force.
Yes, sir.
Whenever this block is released by pushing with a force F, then the block comes to this position and it is under equilibrium under the action of this applied force.
Yes, sir.
Okay? Whenever it is under equilibrium, then the block displaces through a distance x1, means the spring compresses by x1. No?
Yes, sir.
At that time, as the block is under equilibrium, F plus m1z is equal to spring force Fs.
Yes, sir.
Here, Fs on the first block.
Yes, sir.
On the first block here, you see, here I have written F plus m1g is equal to Fs. Okay, that is one equation. Next, for this block to lift upwards, the spring force must be developed is equal to m2z, no?
Yes, sir.
It is spring force develop kavalante. Spring force, what is the amount of spring force to be developed to lift the block? Means the spring force developed Fs dash must be equal to m2z. Fs dash is equal to m2z. That is equal to kx2. That means whenever the extension, you see, whenever compression is there, spring force pushes the block m2 downwards. There is no lifting. Okay. Whenever the spring is extended like this, then spring force acts on the spring force developed on the spring pushes the block m2 upwards. That's why it must be extended above the natural length. It must be extended. Because we push the block downwards with a force F, so that it is compressed. The spring is compressed by length x1. And when it is released, you see, you listen carefully. Whenever the applied force is removed, the spring force developed in this pushes the block upwards so that it raises up to this point. Beyond that, it cannot rise.
Sir, again it will come to original position. Okay.
Here it is the original position now.
Yes, sir.
It is only original position. But we applied here, we see the extra force we applied now.
Yes, sir.
We applied extra force. That's why here it pushes downwards up to certain distance x1. And when you release them, then the spring pushes the block upwards so that whenever it come back to the original position here, whenever it come back to the original position, then the force acts on the block is only M1Z. No spring force develops.
Okay, sir.
Isn't it? Whenever this block comes to the original position, weight M1Z only acts and no spring force is there. Because whenever the block comes to this position, the spring is in natural length. It is natural length. That's why no spring force is developed. But while moving upwards here, because of work done by the spring force on the block upwards, some work is done so that the block acquires some kinetic energy whenever it reaches this position, original position.
Oh, yes, sir.
But
Okay,
because
sir.
of inertia of motion, again it move upwards, and when as long as the block move upwards, in such case, the spring force developed in the spring pulls the block downwards, and weight M1Z always acts, that also downwards, and the work is done against their motion, and the velocity becomes zero after it rises up to certain distance, say x2.
Okay.
Okay. Now velocity becomes zero at this point. So in this case, what is the work done? According to Verken's theorem, I calculated from this position A to C. When block travel from A to C, I applied the work energy theorem from A to C. From A to C, when the block moves, I applied the work energy theorem. According to the work energy theorem, I got. Okay.
Okay, sir.
Now,
Thank you, sir.
okay, welcome. The video shares Jack. వీడియో షేర్ ఆపేసేమని చెప్పాను, నింపేయట్లేదా? చెమట ఉన్నా మీకు? రైట్. Shall I erase this one? Okay, next you see another problem. All of you see the next problem here. All of you see 8th problem. Consider the situation as shown in the figure. There is an inclined surface with angle of inclination 37 degree. Okay, one spring is fixed at the bottom, like this. One block is kept on the inclined surface. The block is kept at the position A. Okay, have you seen the problem? Now, all of you see the board. All of you see the board. Here, as you see the diagram, you can understand. Because in previous case, the block is displaced through a distance x1, and when you release the applied force, when you make the applied force zero, then the block raises up to certain height. That raises up to x1 plus x2 height, it rises. That's why work done against the gravity is minus m1g into x1 plus x2. No, minus m1g into x1 plus x2. Okay. Next, you see this problem. Consider the situation as shown below. The block is released from position A. The block is released from position A and compresses the spring by 20 centimeter. You see, whenever the block is released, here friction is also there. While the block is moving downwards, then friction acts on the block opposite to their motion in upward direction. Of course, kind of friction is there as the block is moving. As long as the block comes down here, then of course, whenever the block is released, as the block comes down means definitely weight component mg sin theta. No? Of course, weight mg acts vertically downwards direction. Normal reaction mg cos theta. Because if it is theta, this is theta. That's why it is mg cos theta acts in this direction. Normal reaction n acts in this direction. When you release the block, as mg sin theta greater than fa, then only the block comes down. Whenever the block comes down here, then velocity gradually increases, and whenever it just touches the spring, then the spring starts compressing. Whenever the spring starts compressing, then the spring force acts on the block in opposite direction. Due to that, the speed of the block gradually decreases, and whenever the spring compresses by certain length, say x1, then the block comes to rest momentarily. After that, the spring compresses. In first case, the spring compressed by 20 centimeter is given. 20 centimeter. Here, whenever the block is released, the block comes down with acceleration, and whenever the block touches the edge of the spring, then the spring starts compressing, and whenever the block here the spring compresses by a length x1, then the block momentarily comes to rest. Why it is coming down here? You see, up to this the block comes down with acceleration only. But whenever the block pushes the spring in this direction, the compression of the spring gradually increases, so that the spring force gradually increases. And whenever spring force gradually increases, if it becomes greater than the net force acts on the block downwards, then the velocity of the block gradually decreases, and after reaches the position here, the velocity becomes zero momentarily. After that, as the spring is compressed by x1, immediately the spring pushes the block upwards. When the spring pushes the block upwards, then the block rebounds up to a distance x2 is equal to 1 meter given. X2 is equal to rebound. Okay. The block rebounds through a distance 1 meter. Yeah. The block rebounds to a distance is equal to 1 meter up the inclined plane. Now, what about the find the coefficient of friction and spring constant K between the block and incline? Mass of the block is given as 2Ks. This is the case. Here it is given. Suppose this is the say position B. This is the position of the block B. Say it is B. It is A. So first you consider the motion of the block from A to B. When you consider the motion of the block from A to B, initial velocity here is 0 because the block starts from rest. That's why initial velocity is 0, and whenever block reaches the point B, the final velocity is also 0. As initial velocity, final velocity both are 0, change in kinetic energy is equal to 0. If you know the change in kinetic energy, net work done is 0, no? So here, according to work energy theorem from A to B, net work done is equal to change in kinetic energy, that is equal to 0, because initial velocity, final velocity are 0. Net work done means while the block is coming down, up to what distance the block slides down. I think the distance is mentioned in the, whenever the block comes down, up to what distance the block comes down here, you have to find. You see, here initially between the spring and the position of the block, the distance is given in the diagram only. You see, already I have seen, I think. Initially, from the end of the spring, which is in unstable condition, or compressed, which is not compressed, the distance between the block and the edge of the spring is equal to 4.8 meter. Whenever the spring is compressed by a length x1, then the total displacement of the block before coming to rest is equal to 4.8 plus x1. The x1 is given 20 centimeter. Okay, now you see, whenever the block comes from A to B position, because of weight component mg sin theta, as the block comes down, work is done by gravity. So work done by gravity plus While the block is coming down, as the friction exists, work is done by friction plus whenever the block compresses the spring, some work is done by spring. So work done by spring is also there. These are the, of course, due to normal reaction, there is no work done by the normal reaction on the block. So these are the different types of work done. It is the net work done. That net work done is equal to 0 now. So now you tell me what is the work done by gravity. You tell me what is the work done by gravity from this. Stop your video sharing. What is the work done by gravity? You tell me. You see, before coming to rest, the block travel a distance s is equal to AB, which is equal to 4.8 plus x1, no? 4.8 plus x1 meter. 4.8 plus x1 is given in centimeter. That is equal to 0.2 meter, no? So 0.2 meter. That is equal to 5. 5 meter is the displacement of the block before the block comes to rest. Now you tell me what is the work done by gravity. The weight component mg sin, here actual weight is in this direction, whereas the block is moving in this direction. Along the direction of motion of the block, what is the weight component? Mg sin theta. With this weight component, the block travel a distance equal to s. 4.8 plus x1, that is s. This is a s. So work done by gravity is equal to work done by gravity. Okay, substitute directly. This formula is substitute from 1. This is a 1. From 1. Work done by gravity means mg sin theta into displacement of the block before coming to rest is s. Of course, that is equal to 5. Next, what is the work done by friction? You tell me. Work done by friction. What is the work done by friction? You tell me. Whenever the block travel a distance s before coming to rest, friction acts on the block in opposite direction. That's why minus work, negative work is done by the friction. That's why friction force Fk into displacement of the block before coming to rest is equal to s. It is the work done by friction. Next, what is the work done by the spring? Up to this work done by friction we have calculated. Then what is the work done by the spring? Here, whenever the block comes to this position, then only the spring exerts the force on the block up to a distance x1 before coming to rest. That's why here, as the spring is compressing, spring force acts in this direction, whereas the displacement of the block is in opposite direction. So work done by spring force is negative. That negative spring force is the negative work done by the spring is equal to half k into compression of spring is x1. That's why x1 square. This is equal to 0. This is equal to 0. Now, here x1 is also given. I think everyone is known x. Okay, substitute the data here. mg sin theta into s minus fk means mu into normal reaction acts on the block is equal to mg cos theta. No? mg cos theta into s. Okay, is equal to half k into x1 square. Here you substitute the data. Here in these two, we can take mgs common. No? When you take mgs common, sin theta minus mu cos theta is equal to half k into x1 square. Substitute the data. M means 2k, Z means 10, S means already 5 into sin 37 minus mu means, mu is not given. So we have calculated mu also. So mu into cos 37 is equal to half, k is also not given, k into x1 square. x1 is 0.2 meter, 0.2 whole square. 0.2 whole square. When you simplify them, here when you simplify them, then you will get 60 minus 80 mu is equal to 0.02 k you will get. This is equation 1. This is equation 1. If you simplify them, you will get this equation. You see, sin 37 means we can get 3 by 5. 5 cancel. 3. 3 into 2, 6. 6 into 10, 60. Similarly, here we will get mu into 80. That is equal to k into something you will get. K into 0.02 k. 0.02 k. This is equation 1. It is we got this equation when motion is considered from A to B. No. Next, after it reaches B here, as the spring is compressed by a length equal to x1, then spring force pushes the block in backward direction. That's why the block move from B to A. Because of not B to A, sorry, B to C. Now the block move back to a distance B to C. So when you consider the motion from B to C means the distance traveled in backward direction is equal to 1 meter given in the problem only. Here, whenever the block comes to rest, at that time the spring compresses by a length equal to x1. So now, whenever the block comes to rest, immediately the spring force developed in the spring pushes the block in backward direction. So the block rebounds back, and it travels to a distance equal to x2 is equal to 1 meter, and then it comes to rest at this point. Here it is the point say C. At point C, the block comes to rest. So from B to C, again you apply the conservation of energy. You can apply work energy theorem. According to work energy theorem, why I am applying work energy theorem means here velocity is 0. Whenever it reaches the point C backwards, again velocity becomes 0. Change in kinetic energy is known. That's why change in kinetic energy is 0. That's why according to work energy theorem, net work done is equal to change in kinetic energy, that is equal to 0. Net work done. While the block move in backward direction, as the spring pushes the block in this direction, spring force acts in this direction, and block also move in the same direction. That's why work done by the spring force in this case is positive. In previous case, work done by the spring force is negative. But whenever the spring is compressed here, the spring pushes the block backwards. That's why work done by the spring force is positive. So what is the work done by spring force? Work done by spring force is there. Okay, next. As the block move upwards against the gravity, the block move in backward direction. The weight component mg sin theta pulls the block downwards. But even then the block move upwards means there is a work done by gravity which is negative. Of course, in general I am writing first. Wg plus. While the block move in backward direction, in this direction when the block moves, friction acts in opposite direction. That's why work done by friction is also there. So Wf that is equal to 0. Now you substitute the data. Work done by spring force. You see, whenever the block is pushed back, until the block comes to this position only, there is a work done by the. In previous case, through what length the spring compresses, up to that distance only, the spring exerts the force on the block. After the block comes to this position, when it continues to move in forward direction, in upward along the inclined plane upwards, the block leaves the spring. That's why the spring does the work on the block up to the distance up to which it is compressed previously. That's why positive work done by the spring force is equal to half k into x1 square plus work done by gravity. Here work done by gravity means here whenever the block move in this direction, the gravitational force component acts on the block in opposite direction. That's why negative work is done. That's why minus weight component acts along the inclined plane mg sin theta into displacement of the block. From B to C, whenever the block travel through a distance equal to 1 meter, up to 1 meter, work is done by the gravity which is negative. It is work done by gravity. Next, what is the work done by the friction? Whenever the block move in this direction, the friction acts on the block in opposite direction, so that negative work is done. That's why work done by the friction force is also negative, which is equal to minus Fk into. What about before coming to rest, as the block travel a total distance of x2? So you write x2. This is equal to 0. Now you see, you substitute the data. Half k we have to find into x1. X1 means previously what is x1 given? 0.2 meter. That's why you write 0.2 meter. Square is there, so square plus minus plus into minus mz. M means 2 into z means 10 into sine 37 degree into x2. X2 is called 1 meter given now. So 1 minus Fk means mu into normal reaction mg cos theta. M means 2 into g means 10 into cos 37 into x2. X2 is 1 meter. That is equal to 0. So if you simplify them, then you will get, here you see, you will get 12 plus 16 mu is equal to 0.02 k you will get. It is equation 2. From equation 1, 60 minus 80 mu is equal to 0.02 k. This is equation 1. From these two equations, you solve them. That means when you subtract them, this will be cancelled. When you subtract them, then this will be cancelled. This becomes plus. So when you subtract them, Then you will get, what is the value you will get here? See, minus 60 minus 12. 48, no? 48. Here, as we are subtracting, it becomes plus. So, plus 80 minus 16. 64, no? 64 into mu. That is equal to 0. Or 64 mu is equal to 48. Or mu is equal to 48 by 64. That is equal to 48 by 64 means what is the value? 48 by 64, or sorry, it becomes plus now. Because we are subtracting, it is minus, it is plus, it is a minus. That's why plus means 96 you will get. So 96 you will get. Okay, 96 mu. So after simplification, you will get 1 by 2 now. So it is 96. So mu is called 48 by 96. That is equal to 1 by 2 now. 48 2s are 96. Therefore, mu is equal to 0.5. This is the mu value. This is the mu value. If you substitute the mu value in any one of these two equations, you will get k value. From 1, 60 minus 80 into mu means 0.5 is equal to 0.02 k. Or if you simplify that, then after simplification, you will get k value 1000. K value 1000 you will get. 1000 Newton per meter. This is the k value. In this way, we have to do. Yeah, 1000. Very good. Ashwant. Very good. Siddharth. Ashwant, Rohan. Okay, okay, very good. Leonardo. I think English scientist. Swarantesh. Okay, okay. Swarantesh, what is your doubt? Swarantesh. What is your doubt? Swarantesh, what is your doubt? How you got equal to 4.8? Which one? Swarantesh, I will unmute you. Speak with me. Swarantesh.
Sir, 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 how we got 4.8?
Where?
A to B.
A to?
A to B, how we got up to the spring 4.8, sir?
No, not from A to B. Not from A to B 4.8. Here, initially, whenever spring is in unstructured condition, from the end of the spring up to the initial position of the block, the distance is 4.8 meters. That is given in the problem. Okay.
Okay, sir.
Right now. Right. Next one. You see the next problem. All of you see the next problem. All of you read the next problem. So all of you read that problem. Okay, all of you see the board. All of you see the board. Figure shows two blocks A and B. Figure shows the two blocks A and B. This is A and this is B. Figure shows the two blocks A and B. Each are having mass 320 grams. That means 0.32 kg. Is connected by a light string passed over the smooth, light, frictionless pulley. The block A is kept on the horizontal surface. Okay, on which the block A can slide on smooth surface. The block A is attached to the spring of spring constant 40 Newton per meter. Here it is a spring of spring constant 40 Newton per meter. But whenever the block is at A, here, whenever the block is here, the block M1 is here. At the time, the block is connected to one end of the spring. The other end of the spring is fixed to rigid support here. Okay, now here to this block of mass M1, by means of a string. Actually, initially, whenever the block is here, the spring is connected like this, so that spring is vertical and it is in unstretched condition. That means this height of the support from the bottom, that is equal to natural length of the spring also. Okay, now to the block, one end of the string is connected here. The string is passed over the light frictionless pulley, and other block is fixed here. Okay, when you release the block, when you release this lower block M2, then immediately this block is pulled in this direction. Okay, as long as the block is pulled in this direction, the length of the spring, whenever the block M1 is at this initial position only, or at this position P only, at that time spring is unstretched condition, so that no force acts on this, no force developed in the spring. But whenever the string pulls the block in this direction, the length of the spring gradually increases like this, and whenever this block comes to this position A, at that time the spring position is like this. With vertical, it makes an angle theta. The spring makes an angle theta with vertical. At that time, the block is M2 here. Suppose here, whenever the block is at A, the block displaces through a distance equal to say D. Then here initially the block is here actually. But whenever the block is released, if it comes down through a distance D, then this block moves through a distance D in this direction, because both blocks are joined by means of inextensible string. To what distance this block M2 comes down, to the same distance this block will displace in this direction. So the displacement of the block in this direction is equal to D. Okay, now in this case, the spring occupies the position like this, so that it makes an angle theta with vertical. Suppose in this case, the length of the string is say L. The length of the string is say L. The length of the string can be calculated, no? Initially, whenever the spring is like this, it is in unstretched condition, so no spring force is developed. But whenever the block is here, the spring occupies the position like this, so that its length is greater than natural length of the spring, H. Okay, that's why what is the length? What is the extension of the spring whenever the block is here? Extension of the spring whenever the block is here is say X. Extension. Extension in spring. X is equal to the final length of the spring minus original length. That means L minus X. It is the extension of the spring. Because of extension of the spring, some spring force is developed. A spring force pulls the block in this direction. So you resolve the spring force into components. One component in this direction, another component in this direction. If it is theta, definitely it is theta. So this is spring force Fs cos theta. Here it is Fs sin theta. Fs cos theta and Fs sin theta. Here, whenever the block displaces like this, the spring force acts on the spring force component acts on the block in this direction. One spring force component acts vertically upward direction. Here they asked, find the velocity of the block A at the instant when it breaks the surface below. You see, as long as the block move in this direction, then theta value increases. Then theta value, here we see, the theta value gradually increases. Whenever theta value increases, then Fs cos theta value. You see, whenever the block move like this, initially whenever the block is here, the spring force Fs cos theta, if there is no spring force, that's why Fs cos theta is 0, F sin theta is also 0. As long as the block move in this direction, the spring force starts acting on the block vertically upwards and along horizontal direction also. So whenever the block move in this direction, opposite the motion, the spring force component Fs sin theta acts in this direction and Fs cos theta acts in this direction. Okay, here at the instant whenever this block breaks off the surface, or at the instant whenever this block leaves the contact with the floor, smooth floor. Okay, this is the floor. Whenever the block leaves the contact with the floor, it is a smooth floor. Smooth. So whenever the block move in this direction, then the spring force acts on the block whenever balances the weight. Weight M1z acts vertically downwards direction. Weight M1z acts vertically downwards direction. Whenever this Fs cos theta is equal to M1z, then immediately, you see, as long as the block move in this direction, Fs cos theta component here acts upwards and this is downwards. Whenever Fs cos theta balances this M1z, then the block starts rising upwards. Whenever it further moves like this, then this becomes greater than this one, so that the block lifts. Then, whenever the block ready to leave or just starts lifting or breaks the contact with the floor, at the time along vertical direction net force must be 0. That's why when block leaves contact or breaks contact with the floor, at that time Fs cos theta must be balanced by weight M1z. Fs cos theta must be balanced by weight M1z. Fs means, you see, suppose whenever the spring occupies the position like this, the extension of the spring is equal to L minus X, no? So X is the extension of the spring. That's why Fs can be written as K into X into cos theta. Here the block loses contact with the floor at the instant whenever spring makes an angle 30 degrees. That is given in the problem only. You see, that is given in the problem only. In the problem only, in the diagram only it is given. Find the velocity of the block at the instant when it breaks off the surface below it. So whenever theta is equal to 30 degree, at that time the block ready to leave. That's why theta is equal to 30. So cos 30. 30 only is equal to M1. M1 means 0.32 kg now. So 0.32 into G means 10. So K value is also given. We substitute here K 40 into what about X value? What about extension of the spring? extension of the spring we have to calculate. So extension of the spring is equal to x we have to calculate into cos 30 means root 3 by 2 is equal to 0.3 means 3.2 you will get. Therefore, from this, what about the x value? From this, what about the x value? So you find x value from this. X is equal to 3.2 into, okay, 220s are. 220s are. Therefore, x is equal to 3.2 by 20 root 3. This is say 1. But from this, it is say 2. It is say, okay, it is say 1. From 2 and 1, here it is h no. Original length is this one, final length is this one at the moment whenever the block leaves the contact with the surface. That's why L minus this h, that is the extension of the spring. That's why this is equal to x is equal to L minus h. That is equal to 3.2 by 20 root 3. 3.2 by 20 root 3. Okay, now in this case, what about L value? What about L? We have to find, actually our aim is we have to find the D value. When you know D value, we can calculate the velocity of the black. That's why D we have to find. To find the D value, we have to know this L value. So from this L is equal to 3.2 by 20 root 3 plus h we can write now. This is equal to 0.4 meter. That is equal to 3.2 by 20 root 3 plus 0.4 meter. Here, because of, you see, theta will increase when theta will, fs is not constant, no. Here this fs cos theta value is not increased because of theta. Whenever the block move in this direction, here some Rakshit you asked now. Whenever the block move in this direction, extension gradually increase. Whenever extension increases, the spring force developed in this gradually increase. When spring force increases, then fs cos theta value gradually increase upwards. This increase in fs cos theta value is not because of theta, because of fs. Okay, Rakshit. Whenever the block move in this direction, spring extends. Because of extension, fs increases. Due to fs increase in fs value, the increase in fs value is more than decrease in cos theta value due to increase of theta. That's why there is a net increase in fs cos theta. Whenever this fs cos theta balances the weight component, weight m1z, then at the time the block starts leaving the contact with the floor. At the time, what is the speed of the any block? Because both blocks move with the same speed, as both are joined by means of a inextensible string. Okay, from that we can calculate the L value, no? From that we can calculate the L value. If you know L value, then D value. You see, from this right angle triangle, it is D value, no? This is D. So from this right angle triangle, you take sin theta. Sin theta is equal to opposite by L. Sin theta is equal to opposite means D by L. Implies D is equal to L sin theta. We can write now L sin theta. Therefore, D is equal to L means this one 3.2 by 20 root 3 plus 0.4 into sin theta means sin 30 degree. So you simplify them. If you simplify them, then you will get D value 0.3 meter. D value 0.3 meter. Okay. Here it is, sorry, it is not 30 degree, 37 degree. It is 37 degree. It is not 30 degree, 37. Of course, it is also not given actually. On this formula, we have to find. In the problem, it is not given. We have to calculate. 37 degree we got. Here you see, whenever the block ready to leave, then at the time, x cos theta is equal to, we got 0.32 into 10. kx cos theta is equal to 0.32 into 10. So what about x value? Here we got, here we see this 37 is also not given actually. Of course, in the diagram it is drawn but not given. This 37 is also not given. That's why you don't draw in the diagram. We have to calculate. Fs cos theta is equal to m1z. Fs means kx into cos theta. That is equal to m1 into z. Okay, this is one equation. This is equation 1. This is say equation 2. So next, from the diagram here we see x value we have to find. X value means x value is this one. This is totally L. L minus h is equal to x now. L minus h is equal to x. L minus h is equal to x. So this is another equation 3. Here you see from this 3. From 3, x is equal to L minus h. That is equal to h value is given. What about L value? You see here sin theta is equal to, from this diagram. From this diagram, cos theta is equal to h by L we can write now. Since cos theta is equal to h by L. Okay, therefore L is equal to we can write. L means from this h by cos theta we can write h by cos theta minus h. Okay, this is the relation between h by cos, relation between theta and x. Theta and x. Okay, now from this equation you see kx cos theta is equal to mz. Then what about x value? X value is equal to m1z by k cos theta. No? X value. Therefore, x is equal to h by cos theta minus h. That is equal to, from this x value is equal to m1z by k cos theta. m1z by k cos theta. Okay, in these all terms here, you see h is given, k is given, theta we have to calculate. When you simplify them, theta is equal to 37 degree, you will get. Theta is equal to 37 degree, you will get. Next. So what about d value? So before the block leaves the contact with the floor, at that time the displacement of the block is d. How we can get d value? That is opposite to theta. That's why you take sin. You take tan theta. Tan theta is equal to opposite by adjacent. That means d by h. Implies d is equal to h tan theta. D is equal to h means 0.4 into tan theta, tan 37. That is equal to 0.4 into tan 37 means what is the value? 3 by 4 now. Therefore, D is equal to 0.3 meter. So D is equal to 0.3 meter. That is the displacement of the block when at the moment whenever the block leaves the contact with the floor. So D is equal to 0.5 meter. 0.3 meter. Okay. Now, so whenever the block displaces through a distance equal to 0.3, at that time these two are equal, then the block ready to leave. So now you apply the conservation of our work energy theorem according to work energy theorem, because we have to find the velocity. At the instant whenever the block ready to leave the contact with the floor, at that time suppose the velocity of this block is say v, the velocity of this block is also equal to v only, because both blocks are joined by means of inextensible string. So both acquires the same velocity. Sin 37 is 3 by 4 only, no? Sin 37 is, sorry, tan 37 is 3 by 4 only I wrote. Is that? Okay, right. According to work energy theorem, you see, initial velocity is 0. Initial velocity whenever the block m1 is here, initial velocity is 0. Whenever the block leaves the contact with the floor, at that time velocity of the block is say v. So according to work energy theorem, whenever the block displaces up to a distance d, what are the work done? Net work done is equal to general formula change in kinetic energy half mv square minus half mv square. This is 0 because initial velocity is 0. But whenever the block is here, the kinetic energy of the block is equal to this one. At the same time, this also acquires the kinetic energy. That's why total kinetic energy we have to write. Work done means whenever the block displaces in this direction, as it is the smooth, no work done by friction. No work done by friction. But whenever the block move in this direction, as this block comes down, if this block moves to a distance d, this block comes down to a distance d. That's why work is done on the block m2, which is positive. m2z into d. It is the work. It is only the work done by gravity. As this block move along horizontal direction only, no work is done by the gravity. Only on this block work is done by the gravity. So here there is a work done by gravity is there, plus work done by whenever the block move in this direction, spring force acts in opposite direction. That's why work is done by the spring also. That is equal to change in kinetic energy means half into total mass of the system. As the two blocks travel with the same velocity, then total mass of the system m1 plus m2 into common velocity square. Now, work done by gravity is only on this block m2zd plus work done by the spring. You see, whenever the block move in this direction against the motion of the block, because of the spring force component Fs sin theta only work is done. Of course, opposite to the spring force, as the block moves, negative work is done by the spring force. That negative work done by spring force is equal to Fs sin theta into it is spring force. Here, whenever the block move in this direction, it is spring force. The work done by the block on the work done by the block due to spring is equal to what is the formula? But here the spring force is not constant. As long as the block move in this direction, spring force is not constant. That's why we have to write half kx square now. Because of work done by the spring force, some extension takes place in the spring. Due to that, energy stored in the spring, that is equal to half k into x square. It is the work done by the spring force. Work done by the spring force. Okay. So work done by the gravity is this one, and whenever the block displaces through a distance t, at that time the extension of the spring is equal to x. Due to that, some work is done by the spring. Work is done on the spring to extend by a length x. That's why the energy stored in the spring is equal to half kx square. But at the same time, whenever the block displaces like this, the spring force acts on the block in opposite direction. That's why work done by the spring force on the block is negative, which is equal to energy stored in the spring, half kx square. This is equal to half m1 plus m2 into v square. Now we substitute the data. Here. m2z. m2 means mass of the both blocks are same. M2 means you see 0.32 kg no. So 0.32 into z means 10. D means 0.3 we got somewhere here. 0.3 minus half k means 40 into x means x we got. What is the x value we got? X value. X value is equal to 0.1 meter you will get. If you substitute the theta value here, you will get 0.1 meter. So x value is 0.1. Whole square is there. That is equal to half into m1 plus m2. 0.32 plus 0.32 into velocity square. If you simplify them, you will get 1.5 meter per second. The velocity of each block becomes 1.5 meter per second. So in this way we had to do. First here, whenever the system is released, because of gravitational force acts on the block m2 downwards, m2z downwards, this block is pulled in this direction. Whenever the block is moving like this, as long as the block moves towards right, extension in the spring gradually increases, so that the spring force component acts on the block in upward direction gradually increases. At the instant, whenever the block ready to leave the contact with the floor, at that time, weight and the spring force component both are balanced. Then only it will start lifting. So at that time, they ask the speed of the block. So at that time, what is the extension of the spring? So make these two are equal. So here, Fs cos theta is equal to m1z. From that, Fs means spring force developed. When the block comes to this position, extension of the spring is x. Then kx into cos theta, that is equal to m1z. Okay, but the length of the spring here is L. Original length is unstretched length is equal to h. L minus H is the extension of, that's why X is equal to L minus H. So this is another equation. So from this, X is equal to L minus H. X is equal to, L means we can write H by cos theta. L is equal to H by cos theta. Because from this right angle triangle, you take cos theta is equal to H by L now, then L is equal to H by cos theta we can write now. So instead of L, you write H by cos theta minus H. This is the extension. But from this formula, X is equal to M1G by K cos theta we can write now. M1G by K cos theta. Here every term is known. In this, every term is known except theta. So from this, if you calculate theta, then you will get theta is equal to 37 degree. If you substitute theta value here, then from this equation, you will get X is equal to H by cos theta means cos 37 degree minus H. If you simplify them, you will get 0.1 meter. Because theta value we got. When you substitute this theta value here again, then you will get X is equal to 0.1 meter. Okay, now what about the displacement of the black at the moment whenever it leaves the contact with the floor? At that time, you see, in this right angle triangle, as we know this H value, adjacent side, opposite side we need. Tan theta is equal to opposite by adjacent. Tan theta is equal to opposite D by adjacent side H. Then from this D is equal to this one. Theta value already we got, H value given here. Then if you substitute, then you get 0.3 meter. So that is the displacement of this block or this block downwards at the moment whenever this block ready to leave the contact with the floor. Now, according to Work-Density theorem, whenever the block comes from this position to this position, at that time, while it is moving like this, at the moment whenever it leaves the contact with the floor, at that time, if the velocity of this block is v, the velocity of this block is also equal to v in downwards direction. Okay, now according to Work-Density theorem, whenever the block move like this on this system, on this block, work is done by the gravity. The block comes downwards, and the gravitational force also acts on this block in downwards direction only. That's why work is done by the gravity on this block is positive. Here, no work is done by the gravity because displacement of the gravity is towards right along horizontal direction, whereas gravitational force acts perpendicularly downwards. That's why no work is done by the gravity on this block. So net work done by gravity on the system is M2G into D in downwards direction. And you can D force M2G and D. Because of that weight, it comes down to a distance D. That's why work done by gravity is this one. At the same time, whenever the block displaces through a distance D, as the spring extends by X, then work done by the spring force on the block is equal to energy stored in the spring of Kx square. So it is the work done by the spring force, which is equal to, suppose if any friction is there, then whenever the block moves in this direction, as it is smooth, no work is done against the friction. Suppose if friction is also given, to move the block from this position to this position, against the motion of the block, friction acts in this direction. So work done by friction also we have to add. That is equal to minus Fs. That means mu into normal reaction into S. S means displacement, that is equal to D. Is equal to half m1 plus m2 into v square. Everything is known except v. So you substitute here, you will get answer. Okay. In case of rubber band also, is nothing but that acts as the spring only. Look, Pranit, rubber band also acts like a spring only. Okay, that's why you can use the concept like this only. What, Bala? What is your doubt? Bala, what is your doubt? Come on, hurry up. What is your doubt, Bala? What is spring force? Spring force acts on the spring in this direction. Spring force acts on this developing the spring in this direction because it is extending. Whenever the block move like this, spring force extends. That's why spring force acts on the block away from them. That's why in this direction they acts. Work done by spring force. Whenever the block comes from this position to this position, due to that the spring extends by X. The length of the spring increases by X. That's why work done by this block on the spring is equal to half Kx square. At the same time, the spring also, by applying the spring force on the block against their motion, that also that also spring also done the same work but in opposite direction. That's why minus half kx square. Minus half kx square. Okay, Bala. ఇక్కడ బ్లాక్ ఇటువైపు మూవ్ అయినప్పుడు స్ప్రింగ్ ఎక్స్టెండ్ అయిందంటే this block does some work on the spring. At the same time, the spring exerts the opposite work on the block against their motion. That's why the work done by the block on the spring in extending is same as the work done by the spring on the block. So work done by the spring on the block against their motion is equal to half kx square. Okay. So finally we got this one. Next problem. Next we see next problem. All of you see the next problem. Okay, now all of you look at the board. Next problem, 7th one. There are two blocks kept on the rough horizontal surface. No, smooth only. Two blocks having masses m1 and m2. Two blocks having masses m1 and m2. Both are joined by means of a spring. Both are joined by means of a spring. Okay, here the both blocks are pushed. Both blocks are pushed. Actually, the initial position of the blocks are like this. The initial position of the blocks are like this. But both are pushed so that the spring is compressed. The total compression of the spring is equal to x. The total compression of the spring is equal to x. Total compression. Suppose the total compression of the spring is equal to x. Total compression in spring is equal to x. If the two blocks are pushed towards each other, and whenever the compression of the spring is x, then the two blocks are released. Whenever two blocks are released, here we see, at the instant whenever the spring is compressed, spring force developed, and the spring force pushes the block away, and the spring force developed here pushes the block away like this, so that the two blocks move like this. Two blocks move like this. Here, at the instant when work done on the two blocks, before the two blocks leaves the spring will be. Here you see, whenever the two blocks are here, this is the natural length of the spring. Natural length of the spring. Whenever the two blocks are here, in between the two blocks, spring is there. The spring is in natural length. That's why no spring force is developed. But whenever the two blocks are displaced, suppose this block is displaced by a length x1, this block is displaced by a length say x2. Then total compression of the spring becomes x is equal to x1 plus x2. The total compression of the spring is equal to x1 and x2. Due to that, x1 plus x2. Due to that, spring force is developed in the spring, and the spring force pushes this block in this direction, this block in this direction. Now the two blocks are released. When two blocks are released, the spring force develops, pushes the block in this direction, in this direction, and whenever the two blocks reaches the original positions, at the time, whatever the initial displacement of the two blocks, then the two blocks displaces by the same amount in backward direction, and at that time, the velocity acquired by this block is say V1, velocity acquired by this block is say V2. Velocity acquired by this block is V1, velocity acquired by this block is V2. At the time that two blocks leaves the contact with the spring. So what about work done? In this case, what is the work done by the spring on the block A and block B? They asked. What is the work done by the spring force on the block A and block B? Here you see, at any time before the two blocks leaves the contact with the spring, same spring force acts on this block and this block also. Spring force is constant. Spring force here you see, spring force is the internal force now. Spring force F is equal to change in momentum dp by dt. Whenever the spring force acts on the block is equal to F is equal to dp by dt. This is constant on both the blocks. On this block, same force acts. That's why this is equal to constant. Whenever this is constant, then change in momentum of the system remains constant. Change in momentum of the system remains constant. Or the moment of the first block plus moment of the second block is equal to 0. Change in moment of the first block, change in moment of the second block, that is equal to 0. You see here, actually force means F is equal to final momentum of this block. In general, mv minus initial momentum mu by t. This is the general formula for force. As the force remains same, force acts on two blocks remains same. This is constant. In the same time means it is constant. That's why initial velocity is 0 for both. That's why final momentum of the block remains constant now. Therefore, as the two blocks are there, m1 v1 is equal to m2 v2. This is important condition. So the momentum of the two blocks remains constant at the instant whenever the two blocks leaves the contact with the springs. ఇక్కడ రెండు స్ప్రింగ్స్ వల్ల రెండు బ్లాక్స్ మీద పనిచేసే ఫోర్స్ కాన్స్టెంట్. Suppose in a time t seconds, if the two blocks leaves the contact with the spring, then at any instant of time t, the spring force acts on the block is equal to change in moment of the block. Final momentum minus initial momentum by time. But initial momentum means whenever the velocity of the block is 0, at that time these two blocks are released. So final momentum means mv1 minus mu, u0. That's why mv only final momentum minus 0 by t. As f and t are constant, mv is called constant. For the both blocks, as the spring force remains constant, which is acting on the two blocks for a time t, as ft constant and it is 0, mv is called constant. For the two blocks, before they lose the contact with the two springs, the moment of this block is m1 v1, moment of this block is m2 v2. These two are equal in magnitude like this. These two are equal in magnitude. Now, you apply the work energy theorem because they asked the work done by spring on each block. No, work done by spring on each block. According to work energy theorem, work done on the block. You see, according to work energy theorem, work done on each block is equal to work done by the spring on each block is equal to work done by spring on any block is equal to change in kinetic energy of the block. Change in kinetic energy means momentum square by q into mass minus initial kinetic energy 0. For both the blocks, initial kinetic energy 0. Final kinetic energy is say p square by 2m. Kinetic energy is equal to p square by 2m. For both the blocks, as the momentum remains constant, momentum is same for both the blocks. Final momentum is same for the both blocks. That's why p square is constant, 2 is constant. That means work done by spring on each block. Work done by spring on each block is inversely proportional to mass. Therefore, work done on the block A by work done on block B is equal to mass of block B by mass of block A. Mass of block B by mass of the block A. Okay, therefore, mass of block here, this is the block A, this is block B, say. Then that is equal to, that implies work done by the spring on the first block is W1 by W2 is equal to M2 by M1. This is one condition we got. This is the one condition. Therefore, you apply the work energy theorem according to work energy theorem on the system. According to work energy theorem, you see, whenever the two blocks are released from this position, whenever the two blocks are released from this position, initially the energy stored in the spring is equal to half kx square. The energy stored in the spring is equal to half kx square. Before the two blocks leaves the contact with the spring, at the time velocities acquired are v1 and v2. Okay, now according to work energy theorem, on the two blocks work is done by the spring. On the two blocks work is done by the spring. So net work done by spring is equal to work done by the spring on this block W1s plus work done by the spring on the second block W2s, that is equal to net work done on the spring. Net work done by the spring is equal to energy stored in the spring, work done by the spring is equal to half kx square, so half k into x square. X is the total compression in the spring. X is the total compression in the spring. Okay. Now, so here x1 plus x2 is equal to x, x1 plus x2 is equal to x. It is the potential energy stored in the spring initially. Therefore, what about W1s? You take W1s common in this, W1s of 1 plus W2s by W1s is equal to U. W1s of 1 plus W2 by W1 means M1 by M2, no? It is the work done on this, work done on the first block by the spring, work done on the second block by the spring. Okay, that's why W2s by W1s is equal to M1 by M2. So M1 by M2 is right. So W1s is equal to, when you take LCM, M2U by M1 plus M2. It is the work done on the first block. Similarly, work done on the second block. Work done on the second block by the spring is equal to, you will get M1U by M1 plus M2. These are the work done. These are the work done. Whenever both blocks are shifted to a distance x totally, and whenever released, then what is the work done by the spring on the first block? What is the work done by the spring on the second block? They asked it. So initially, as the two blocks are displaced, so that spring is compressed by x. Initially in the spring, potential energy is stored, that is equal to half kx square. Okay, now whenever you release the two blocks, then the same spring exert the same force on this block and this block. That's why force acts on each spring remains same. That is equal to mv minus mu by t. U is 0 now. Initially both blocks are at rest. That's why 0. Final momentum by time. Here, as the same spring force acts on the two blocks, F is constant. In the same time, the two blocks leaves the contact. That's why E is also constant. Then mv is called constant. That means moment of the two blocks remains constant. Whenever the moment of the two blocks remains constant, then m1 v1 is equal to m2 v2. We can write m2 v2. We can write here. You see, work done by the spring on each block is equal to change in kinetic energy of the block. Change in kinetic energy means final kinetic energy of the block minus initial kinetic energy of the block. As initial velocity is 0, initial kinetic energy is 0. From this, for the two blocks, as momentum is constant and 2 is already constant, work done by the spring on each block is inversely proportional to mass. So work done by the spring on the first block, work done by the spring on the first block, Ws1 by Ws2 is equal to m2 by m1 according to this relation. Okay, therefore, this is one relation. According to work energy theorem, net work done by spring force on the two blocks together, net work done by the spring force on the two blocks together is equal to work done by the spring on the first block plus work done by the spring on the second block. That is equal to, here, that is equal to work done on the spring is equal to change in energy. Change in energy means, you see, here, this spring displaces the block in this direction, positive work. This spring displaces the block in this direction, that is also positive work. So work done by the spring on the two blocks is equal to loss of energy by the spring. Loss of energy means initially energy stored in the spring is equal to half kx square. Finally, whenever the two blocks leaves the contact with the spring, energy stored in the spring becomes 0. That's why change in energy is equal to half kx square. Okay. So therefore, from this we got here work done on the first block by the spring is equal to this one, second block this one. Okay, this is the case. Next, Okay, next one more problem you see. Eight one. So initially, one more problem here. It is the rough horizontal surface, rough surface. Here there is a vertical wall. One spring is connected to vertical wall. Initially, the spring is in unstretched condition. It is the unstretched position of the spring. Unstretched position means it is the natural length. Here one block. Here one block. Here one block is pushed with a velocity v. One block of mass m. One block of mass m pushed towards right, towards the spring with a velocity v. And what is the maximum compression in the spring? They asked. Maximum compression in the spring. Maximum compression in the spring they asked. That is XA. X is equal to how much? You see, whenever the block is pushed in this direction towards right, then at that time, as the block is moving in this direction, the friction acts on the block. Kinetic friction acts on the block in opposite direction. Initially, whenever the block is pushed with a velocity v, at that time, the distance between the spring is free end of the spring and the block is say x naught. That x naught is given. Okay. Whenever the block is pushed towards right with a velocity v, then against the friction, the block does some work, and whenever the block comes to this position, at that time it contacts with the spring and the spring starts compression now. So whenever the block comes to this position, the spring compresses a length equal to say x. Now the block comes to rest. Whenever the block is pushed with a velocity v, then the block moves towards right, and after the spring compresses a length equal to x, then the block comes to rest momentarily here. So this is the maximum compression, because velocity becomes zero means there is no further compression of the spring, because block comes to rest. The block cannot compress the spring further. That's why it is the maximum compression in the spring. So what is that maximum compression in the spring? They asked it. X is equal to question mark. So according to work energy theorem, okay, net work done is equal to change in kinetic energy of the block or change in kinetic energy of the body. Okay, you see, whenever the block moves in this direction, what is the total displacement of the block? Whenever the block moves in this direction, before coming to rest, what is the distance traveled by the block? This is the distance traveled by the block. That is equal to x naught plus x naught. So whenever the block travel up to a distance x naught plus x before coming to rest, what is the work done by friction? Here work is done by the friction, plus at the same time, whenever the block come in contact with the spring starts compression. That's why spring also does some work on the spring block. That's why work done by the spring is Ws. This is equal to change in kinetic energy. Final kinetic energy means whenever the block comes to rest, final kinetic energy is 0. Initial kinetic energy means half m into velocity is v. That's why v square. Initial velocity is v square. What is the work done by friction? Before coming to rest, as the block travels through a distance equal to x naught minus x. Work done by the friction is no doubt friction is in this direction. Displacement of the block is in opposite direction. That's why minus fk into displacement means x naught plus x. What is the work done by the spring? Whenever the block come in contact with the spring starts compression. That's why spring force acts in this direction. So against the motion of the block, as the spring force acts, work done by the spring force on the block is negative. That's why work done by the spring force on the block is minus half k into whatever the compression of the spring, that is x here, so x square. This is equal to, it is the work done by the spring, that is equal to minus half mv square. Okay, therefore minus we can cancel. Fk means we can write mu into normal reaction acts on the block, mg. into x naught plus x. Here plus, as minus is taken common, minus minus cancel. So half kx square is equal to half mv square. Except x, remaining all are known. Then we can calculate x value now. So this is writing the equation is very, very important. Okay, that is the answer. This way we have to do. Next, last problem. Rubber band also acts as the spring only. Rubber band also acts as the spring only. Okay. Okay, next you see. All of you read the problem. Of course, it is a lengthy problem. It may not be completed in this time. Okay. Next class I will take. Okay, right. Have a nice day. If possible, today I will take class to you. If possible. Okay. I am signing out.